This is a video for how to go about doing water pressure calculations for your civil engineering class. As you look on the screen, you will notice that I have created an Excel spreadsheet that will help walk us through the math that we will do in this video. So if you want to pause this video and load Microsoft Excel or Google Sheets and create something similar to what you see right here, it will help you as you go through and do this lesson. So to give us a little bit of, kind of groundwork of what we're going to be talking about, we need to take a look at a water tower. So when you look at this water tower, like in almost any community, you'll see at least one water tower. Obviously you're going to see more water towers in larger communities, but the water has to flow from that tank down to an output source, and that output source might be a supply line at a street. Ultimately, it's going to wind up being at a faucet inside of a home or outside of a house. So you'll notice that 1 pound per square inch of pressure inside of a pipe is equivalent to 2.31 feet of water. So as you look at the water distribution system pipes here, they can be made out of cast iron or cement or PVC pipes. So like the typical distribution pressure in a distribution system, is 65 to 75 pounds per square inch. They're definitely always designed for less than 150. You don't want too much pressure inside of that pipe. You could, run the risk of not supplying water to a community if you don't have the pipe sized right and the pressure sized right. Now within your home, the pounds per square inch of pressure that comes out of any water faucet inside of a house is between 40 and 80 pounds per square inch. As we go through our math today, we're going to determine whether or not our design meets these minimum or maximum distribution pressure requirements. So as we look through and we look at what head means inside of a pipe, it's potential energy. It's water that's not moving. There's water inside of it, there's pressure in there, but it's not moving. And you find that number or that value by subtracting the distance from the source down to where the output of the water would be. So this example question is, what's the static head at a residential supply line if the water level in the elevated tank is 943 feet and the elevation at the supply line is 890 feet? So we're going to go to our spreadsheet and we're going to put in 943 for the water tower, and we're going to put in 890 for the elevation of the site. Now for static water head down here at the bottom, down here in this area is where we're going to do a lot of our, math the numbers we're going to need to do some more larger calculations later. So next to static water head, we're just going to equals, and we're going to tap on 943. We're going to go to minus, and we're going to tap on 890. And we're going to hit enter, and we're at 53 feet of water. Same thing you see right here. Now, in order to find the pressure inside of there, at the slide we looked at earlier, we said, 1 pound per square inch is equal to 2.31 feet of water. We're going to divide that 53 by 2.31. So we're going to go right underneath it for static pressure. We're going to hit equals, tap on that 53 divided by 2.31. And we're going to hit enter. And we're going to get 22.9 and some change. Notice that they went ahead and kind of rounded that up. We're going to go ahead and leave all those sig figs in our spreadsheet number. So back down to water pressure calculations. So notice it says 40 pounds per square inch times 2.31 feet of water would be 92.3 feet of water. So in order for you to have enough pressure, the supply line for your water supply would need to be, above, 90 feet of water. So if you look right here, it says for a minimum pressure of 40, it's going to be just above 90 of what you're going to need. But you'll notice that it says water loses pressure as it travels through that pipe due to friction, and that's known as head loss. So when something's traveling through a pipe, it has to go up against different types of pipes. It has to move through this system, and it's going to lose pressure as it goes through that system. So when you see major losses, it's basically friction for the length of the pipe, and then the minor losses are all the little bends and fittings and valves everything has to go through. And to calculate head loss, you would use something known as the Hazen-Williams formula. And you'll notice that these constant numbers that are given, the 10.44, there's some exponent values of 1.85 and 4.8655, those are givens for the formula. The variables will be the length of the pipe, the flow rate. There's a constant we'll look at what the type of pipe we use, and then there's the diameter of the pipe. So we're going to look at the constant first. And the constant is, what is the material of the pipe made out of? So if it's a brand new pipe, you would use a clean brand new pipe value right here because there hasn't been any water going up against it. For the sake of this video, we're going to look at cast iron and wrought iron pipe, and we're going to use a typical value of 100. If you were using these generally, you would use these numbers over here on the right. So we're going to go to our Hazen-Williams constant right in here, and we're going to put in 100. And I'm going to go ahead and hit enter. I go down here to calculating head loss again, and you're going to say you need the equivalent length for each fitting, and this gives you an idea of these kind of fittings and valves. You can see it going from one pipe to the other, and the water loses pressure as it goes through each one of these valves. And there is a sheet that you can use in an engineering formula sheet. Let me scroll down here real quick, and you're going to see the equivalent length of generic fittings. And for the sake of this video, we're going to be using a 10-inch diameter pipe, and you're going to say that if you have so many different types of, let's say, elbows and T's, this is the equivalent length of a 10-inch diameter pipe for these elbows. And we'll get into a little bit of what this means here in a second. So if we go back here to our video, you'll notice that we want regular 45-degree angle T's. In this case, the equivalent length is going to be 9 for a 10-inch diameter pipe. So for a 10-inch flanged cast iron water supply line, let's go ahead and go back to our spreadsheet real quick. And the diameter of the pipe is 10 inches. Let's put a 10 in here. Now let's go back to our question. It says the pipe between the water tower and the meter includes 7 regular 90-degree elbows, 3 line flow T's, 11 branch flow T's, and 6 gate valves. So you need to find the equivalent length for each one of these. You'll notice that each one of these values is taken from this chart. So you can go through and say, I got so many long radius 90 T's, branch flow T's at 10. So notice, let's give an example. For branch flow T's, 10-inch diameter, it's a value of 30. So if we go back here, set 11 branch flow T's, equivalent length of 30. We're going to go back to our spreadsheet, and we're going to do a little bit of math. You can ignore this 3.2 up here for now. Notice that I've put the quantity next to the equivalent length. So I'm going to hit equals, and I'm going to tap on the 7, and I'm going to go times, and I'm going to go to 14. And I'm going to hit enter. And that gives us an equivalent full length of pipe of 98. If I go back here, you'll see the 98 over here on the side. Instead of going back and hitting equals and going through each of these, I'm going to show you a small shortcut. We already have this 98 right here. And since I have all these right next to each other, Excel is going to take a logical approach and say, I can just take each one of these next to each other and just multiply them out for you. So just have the 98 highlighted. Don't double click inside of it. Just tap and have it highlighted, and you're going to see when I just drag my mouse, I'm not clicking and dragging, I'm just leaving my mouse here. You see this black plus. I'm going to click and drag down and let off until I'm next to the 6 and the 3.2, and it's going to go ahead and do those calculations for me. I didn't have to go in and hit equals and do all that other stuff. I automatically have all of this calculated. You'll notice that I have the exact same values that you see in this chart. Let's go on to finding the length of the pipe before it meets each one of those fittings. So you'll see we have 3.2 miles. There's 5,280 feet in a mile. We're going to do a unit conversion real quick. So when we're here in Excel, I'm going to hit equals, and I'm going to type in convert. And I'm going to double click on convert. You're going to notice it kind of bleeds over into this. Now I'm going to have to type in H4. I'm in cell H4. So I'm at H4, and I'm going to hit comma. And basically it's going to start saying, what are we going from? So you can scroll down over here on the side and you can see statute mile. We're just going to double click on that, and I'm going to hit comma. And you can find feet in here as well, but just so you know, you can hit quotations FT, quotations, close parentheses, and hit enter. And I'll get 16,896 feet. That is the exact same value you see right here. We need to add this value plus our equivalent lengths of our fittings that we just did. We're going to go back to Excel, and I have the total length sitting right here. I'm going to hit equals and type the word sum. I'm going to double click on sum, and I'm going to highlight over the top of all these red numbers, and I'm going to hit enter. We get 17,358.8. When we go back to our presentation here, you'll notice we have 17,358.8. That is our full length of pipe that the water is traveling through. So let's go back to our presentation. We're going to go down here to head loss, and it's going to give us something it hadn't really given us before, and that was the flow rate. So the Q in here is flow rate, and they're going to have that at 110. So next to flow rate, we're going to put in 110. I'm going to go ahead and hit enter. Now we have basically everything we need up here at the top to go through and do our head loss calculation, and that is where our Hayes and Williams formula comes into play. So we're going to hit equals, and I'm going to have you start parentheses, and we're going to type in 10.44. You're going to hit times. You're going to go up to your equivalent length. You're going to say times again. Another parentheses. Q is the flow rate of the water, so 110. Shift 6, that's a caret for an exponent, 1.85. Close parentheses twice. Divided by. Start parentheses. you're going to see C times 1.85. So we're going to start here. We're going to go into C, where we have Hazen-Williams constant. Our constant is 100. Shift 6, 1.85, close parentheses. Actually, you know what? We need to go back into here real quick. I want to put one more parenthesis before this. I apologize for that. Tapped in here, you can see this is black and now it's red. We're going to go, now we're going to say times D for diameter of the pipe. Pipe diameter. I'm sorry, we have to start a parenthesis first. Sorry about that. Shift 9. We're going to go to diameter. Shift 6. 4.8655. We're going to close parentheses twice. So as I kind of went through, I forgot to put in some parentheses as we started. You see where we're trying to separate the values and do our exponents. So this is what a Hazen-Williams formula looks like in Excel. I'm going to hit enter, and you're going to notice we get 2.946. That's the exact same value we get through a regular calculation. As we go through and we do these, this will start making more sense why using this in Excel is a good benefit. So when we go back to our spreadsheet here, we're going to go back to our definition, and it's dynamic head equals static head minus the head loss. So we have 53 up here at the top. We're going to hit equals, tap on our 53, minus our head loss. Enter. So that's a total of 50 feet. So notice that it's going to decrease the pressure as it travels through all that pipe. This is the numeric value to what, pressure is lost as it travels through all of that pipe. When we go back to our definition here, our actual pressure is the dynamic head divided by 2.31. So let's go back here. We're going to hit equals. Our 50 divided by 2.31 comes out to 21.66. Now, does that meet the requirements? According to what we had before up here at the top, we're at 21. No, it does not. Not even close. So what we can do now is we can say, you know what, we need to go back and redesign or do some things that are different. Let's go back to this example right here. It says the water level in the water tower supplying the home in the previous example is 1,487 feet. It says the water level, and you're going to change up the water level and do some different things. So you're going to notice how they come in and do, some different calculations, but it looks like they're kind of keeping with some of the same numbers. We're going to go back and change the top numbers. So it says 1487. Let's come up here. 1487 minus 1246. If we come back to here, we have 103.1. We just changed two numbers, and they went ahead and rounded up to 0.1. It looks like now, we're a little bit above the pressure, but we were able to go through and just find all of our, numbers that we needed and all of our calculations just by changing some numbers up here at the top. This is the benefit to using an Excel spreadsheet. If we said, let's decrease the flow rate, to 100, it doesn't change it too much, but you can go in and change your values of your design to try to find your desired output. So in Microsoft Excel, you're able to go in and set up a framework for your water pressure calculation design as you go through and select your fittings, select all your branch tees, and even select the distance of the pipe. So this has been a video for how to go about calculating water pressure calculations in Microsoft Excel for your civil engineering and architecture class.